what else can be done with the ideal gas law? So, you know, the ideal gas law is PV is equal to nRT. But if we look at N, the number of moles, we know that the number of moles can be calculated as grams divided by the molar mass. Remember that molar mass is grams per mole. So grams divided by molar mass. And just for abbreviation's sake, I'm going to abbreviate molar mass capital mu, the Greek letter mu. So if I substitute this value in for N, PV is equal to grams RT over mu, molar mass. So to calculate, do the molar mass formula first. Mu is equal to GRT over PV. And just multiply both sides by mu, then divide it by PV, and I get that formula. But recall, G over V, okay, mass over volume, is equal to density. Mass over volume is density. So grams per liter. So this is the same as dRT over P. So the molar mass of an ideal gas is equal to the density times the ideal gas constant times the temperature in Kelvin divided by the pressure in atmosphere. And then that's how you can calculate the molar mass of a gas. But again, if you do algebra, you get D is equal, D is equal to P times the molar mass divided by RT. So the density is equal to the pressure times the molar mass of the gas divided by the ideal gas constant times temperature. So application of something else that you can do from using the ideal gas law, which is calculating molar mass. So this particular question, it's got a 2.10 liter vessel, contains 4.65 grams of a gas at 1 atmosphere and 27 degrees Celsius. What is the molar mass of the gas? Recall, the molar mass of an ideal gas is equal to dRT over P. Dirt over P. Okay, dRT over P. We have, and we know that density for gases is measured in grams per liter. We have grams. We have volume. The ideal gas constant's a constant. T. We have temperature, Celsius. I'll have to convert that to Kelvin. Pressure. 4.65 grams divided by 2.10 liters. That will give us a density of 2.21 grams per liter. Substitute that in above. 2.21 grams per liter times 0.08206. Make some room. Liter atmosphere per mole Kelvin. And the temperature in Kelvin is 300 Kelvin. And the pressure is 1 atmosphere. Liters cancel. Atmospheres cancel. Kelvin cancels. And you're left in units of grams per mole, which is what a molar mass is. If I do those calculations correctly, I get the molar mass to be 54.4 grams per mole. Partial pressures. Well, partial pressures work in a similar way to how you would calculate pressure for an individual gas. But what a partial pressure is the pressure of a component of a gas mixture. So the partial pressure is whatever the pressure is of a component. For air, for example, has nitrogen, oxygen, carbon dioxide, argon, various other components in it, and the partial pressure of nitrogen would be the pressure of the nitrogen component, and so on. So it can be calculated two ways. If you know the fraction and if you know the total pressure, you can calculate the partial pressure. So if you know the fraction amount of the component, you multiply that by the total pressure, and that'll give you the partial pressure. So that'll be a new way. And then the other way is if you know the number of moles, of gas, then you can know what the pressure is going to be if you know volume V of your container, and you know the temperature in Kelvin, of course. Just like the ideal gas law, if you know 3 of the 4 easily measurable quantities of a gas, you can calculate the unknown one. And then next, because when gas particles collide, they just rebound off of each other. They don't change their identity, at least ideal gases don't. The sum of the partial pressures, this equation below, will give you the total. So for example here, just say you had 3 components in a mix, you add the partial pressures of those 3 components up, that'll give you the total pressure. And again, why you can make that so the total pressure, the reason you can do that is ideal gases behave independently. Talked about a little bit earlier, calculating partial pressures. If you know the mole fraction of a component in a gas mixture, you can calculate the partial pressure of that component. And well, just for definitions, what the mole fraction is, it's a ratio of the moles of a component, gas in a mixture, so the moles of a component compared to the total number of moles. Symbolized by the equation here. Okay. Greek letter chi for mole fraction. Your component that you're interested in, the moles of it, divided by the sum of the total moles in the mixture, that will give you your mole fraction. You can use that term to multiply it by the total pressure to figure out your partial pressure. Application. So if you have a sample of natural gas, it contains 8.24 moles of methane, CH4, 0.421 moles of ethane, C2H6, and 0.116 moles of propane, C3H8. We've got a mixture that contains those molar amounts. The total pressure of the gas is 1.37 atmospheres. What is the partial pressure of propane? Previously, we've seen that the partial pressure of some component in a gas mixture A is equal to the mole fraction, Greek letter chi, of A times the total pressure. Total pressure is given, and we're given molar amounts of each of these gases. So we can figure out what the mole fraction is of the component A. In this particular example, the question's asking for propane. So we've got 8.24 moles methane. We've got 0.421 moles of ethane, C2H6, and you've got 0.116 moles of propane. Resize everything. That'll give the total pressure, which is 8.777 moles. If we're going to be picky about sig figs, we need to track it to 2 decimal places, since this was an addition problem. Then the mole fraction of propane is going to be equal to 0.116 moles over that total. Do that math correctly, it's 0.01321 moles, but 3 sig figs. That's the mole fraction of propane. We've got the mole fraction, got the total pressure, plug and chug. So 0.132 times 1.37 atmosphere that's going to give a partial pressure of propane to be 0.0181 atmosphere. That's the partial pressure of propane in that mixture. This workflow up above should be pretty familiar to you by now in a general sense, whereas you've seen that this part is usually you are given some amount of some chemical in grams, convert it to moles, then you convert it to moles using a balanced chemical equation, the molar coefficients from it, and then you converted moles to grams. Well, with gas laws, you can do the same idea, but you can convert to those measurable quantities of a gas. So it's an adaptation to the stoichiometry workflow that you've seen many times in your chemistry career at this point. Also, what you can use is if you've got STP, so STP is standard temperature and pressure, which is, if you need a refresher, standard temperature is 273 Kelvin, 0 degrees Celsius. Standard pressure is 1 atmosphere. So if you have that, you can convert volume to moles directly using this equality. And we'll do an example of that on the next slide. So a gas law stoichiometry problem. Lithium reacts with nitrogen gas according to the reaction below. 6 moles of solid lithium will react with 1 mole of nitrogen gas to yield 2 moles of lithium nitride solid. What mass of lithium reacts completely with 58.5 milliliters of nitrogen gas at STP? So at STP, when you see that, it means you can use that 1 mole of gas is 22.4 liters, has that volume. You're allowed to use that. So the question's wanting you to go from nitrogen gas to a mass of lithium. So that's the conversion, or that's the path. Got to go from the nitrogen, the gas phase, to lithium. So we're given 58.5 milliliters of nitrogen gas. Our conversion above is in liters. This has to be liters. 1,000 milliliters in 1 liter. Now we can use the conversion. 22.4 liters in 1 mole. Of nitrogen gas in this instance. That's our ideal gas. So we're moles of nitrogen, the chemical that we're going to convert to is lithium. And we can see that from our balanced chemical equation, 1 mole of nitrogen gas reacts with 6 moles of lithium according to the balanced chemical equation. Then the question is asking for lithium in grams. Solve the periodic table for the molar mass of lithium. 1 mole of lithium weighs 6.941 grams. Units cancel, left in grams of lithium. If I do that math properly, I get 0.1087 grams of lithium. But if I round that to 3 significant figures, get 0.109 grams of lithium. That's an example of a gas law or a gas stoichiometry problem. You can use gas laws to get to moles. Use your balanced chemical equation to interconvert between moles of product, reactant, just whatever the question's asking for, and then solve.